Okay, so I think we're 1 minute early. I said, oh no, it's 1:05. Perfect. So now I'm just on time. So welcome. The end of last lecture, I had done a single example of matrix multiplication. So this was by the definition of matrix multiplication. That is, if you have matrices using the familiar notation here, A times B was defined to be A times B is, so A is M by N, and B is N by P. Okay, and it has to be of this type. So the columns of A and the rows of B have to match. And if they don't, you can't multiply the two matrices. So yes, some matrix products are undefined. You can't just take two matrices and slap them together and think that you're going to be able to multiply them. They have to match up in this way. Okay, and so B has P columns, so call those columns B sub 1, B sub 2, all the way to B sub P. So there they are. And then this was the matrix that you got by taking your time and multiplying the matrix A by each of these vectors. Okay, so the first column you get, this is a vector. It's A times the vector B sub 1. And then the next column you get, sorry, there shouldn't be a comma here. The next one you get is A times B sub 2, and so on all the way to A times B sub P. So there are P columns. These columns are going to have M entries. So if A is M by N and B is M by P, this is going to be an M by P matrix. Okay, so we checked that with the example that we did last time. So another way of thinking about this is each column of AB is a linear combination of the columns of A using the corresponding, or using weights from the corresponding columns of B. Okay, so that's how this is formed. Okay, now this is the definition. There's nothing wrong with this, but it turns out that it practically and actually computing these things, it makes sense to think about it in another way. So there's what's called the row column rule for computing the product. So I'm going to write it out, even though having it written out in this way might not seem that useful to you on first glance. I will show you visually what it is I'm doing here. So row column rule for computing AB. Okay. So what does this say? So if the product AB is defined, okay, then the entry in row I and column J of AB is the sum of the products of corresponding entries from row I of A and column J of B. Okay. So let AB sub ij denote, why is this denote? Denote the ij entry of AB. And if A is an M by N matrix, then the ijth entry of AB is A sub I1 times B sub 1j, the ones have to match up here, plus A sub I2 times B sub 2j plus, and so on, all the way out to A sub in times B sub nj. This is the important bit. Okay. Now, seeing it written like this might be confusing. There's reasons for looking at it this way and computing generally with this. If you're trying to prove something about a general matrix, this is a nice thing. But in actually computing with this, it can be a little frustrating to look at an expression involving a bunch of i's and j's rather than actually seeing some examples. So here's an example. I'm just going to make this up off the top of my head, so maybe the entries are not going to be nice as would normally be when I use an example that comes directly from the textbook. So let's do an example. Let's compute A times B, where let's say A is a 3 by 3 matrix. So let's say we have a 3 by 3 matrix here. What do I want here? So let's say 3, 0, minus 1, 1, 2, 0, and we'll say here I'll put 4, say minus 1 and 1. Okay, so there's our matrix A. And B, what size do I want B to be? Let's see here. So I want it to be, let's make it a 3 by 2. Okay, so 3 by 2, we would still be able to multiply here. Okay, so, and what would the result be? Well, so these have to match, so that's good. And the result would be a 3 by 2. Okay, so what do I want B to be? Let's say column-wise, 1, 2, 3, 0, 1, minus 2. Okay. All right, so here's our two matrices, and I want to find A, B. Okay. Now, note, BA is not defined. So questions about whether A times B is equal to B times A, it's not, because B times A is not even defined. What if I came up with a product such that B times A was defined? Would they be equal then? No, not generally, right? So not generally. Okay, so B times A is not even defined because 2 doesn't match up with 3 once those would be on the inside. Okay, so now that I'm computing A times B here, let's have a quick look at this computation. So how do I want to use this row column rule that I wrote? How do I want to use it here? What do I do visually? So the way that I like to think about this, the way that I've always done this, is I am trying to compute this thing entry by entry. Okay, so it's going to be a 3 by 2 matrix. And so as a 3 by 2 matrix, I'm going to give myself some room here. This is going to be a 3 by 2 matrix. So it's going to have 6 entries. I'm going to compute them. I probably didn't give myself enough room here. Okay, so maybe I should, let's forget that I wrote this. I'm going to give myself like a ton of room here so I can really write it out. So A times B is, I'm just going to write this side. I'm not even going to box myself in here. So I am in the upper left corner. That is first row, first column. What do I do? The row column rule says that since I'm computing A times B, I take the first row of A and the first column of B, and what I do is I think of taking this row of A and flipping it and matching it up entry by entry, multiplying those entries, and summing the result. What do I mean by that? So I take this row, 3, 0, minus 1, think about flipping it and lining it up with this first column of B and doing 3 times 1 plus 0 times 2 plus minus 1 times 3. So to see how that looks, this is 3 times 1 plus 0 times 2 plus minus 1 times 3. Okay, that's what I've done there. And that is a single entry. This is one entry here in my matrix. This is AB sub 1, 1, right? That's what this is. This is the entry in AB in the first row, first column. Okay. All right. So in the next slot, what do I do? So in my next slot, I'm still in the first row. Now I'm in the second column. So I still keep to the first row of A, but now I move on to the second column of B. So I take this first row of A and I flip it in this way, line up those entries, and write out this expression. So I get 3 times 0, okay, plus 0 times 1, plus minus 1 times minus 2. And this entry is AB 1, 2. Now you might say, wow, this is a lot of paper space you're taking up here, and I can barely read what's going on here. Okay. So yeah, someone asked, is this the dot product? Yes, it is. So there's of course a way of writing this in terms of the dot product, which we'll talk about later. But yes, if you're familiar with the dot product, this is the dot product. Okay, what you're doing is you're treating the rows of A as vectors, you're treating the columns of B as vectors like normal, and you're dotting those vectors. That's exactly what you're doing. Okay, well that's good. So a couple of you are checking matrices here, so we'll see after we compute these if we actually get the same thing. So once you get used to this process, of course, you're going to do this all at once. You're not going to write out these steps. This was just to show you how it's going to do. I'm going to write out one more, and then I'm going to do the rest of them quickly. So one more here. Now I'm in this entry, which is second row, first column. So I take the second row of A, first column of B, do the same thing. I flip this and match them up. So 1 times 1 plus 2 times 2 plus 0 times 3. So 1 times 1 plus 2 times 2 plus 0 times 3. And that entry would be AB sub 1, or sorry, sub 2, 1. Okay, so now I'm just going to compute the rest of these. So now I'm in second row, second column. So 1 times 0 plus 2 times 1 plus 0 times minus 2, that's 2. And in this spot I have, so now I'm using third row, first column. So 4 times 1, that's 4, plus minus 1 times 2, that's 4 plus minus 2 plus 3. Okay, so 7 minus 2, so that's 5. Okay, and then the last entry is the third row, second column. So third row of A, second column of B. So 4 times 0 plus minus 1 times 1 plus 1 times minus 2. So minus 1 plus minus 2, so that's minus 3. And so let's compute what this thing is. So 3 plus 0 minus 3 is 0. Here I have 3 times 0 plus 0 plus minus 1 times minus 2, so that's 2. Here I have 1 plus 4 plus 0, so that's 5. 2 and 5 minus 3. So that's my product here. Is that what everyone got? 0, 2, 5, 2, 5 minus 3. Yep, that looks like what everybody got. So that's good. Okay. And yes, that would be helpful, especially when most of the time I will pick examples from the textbook so that I, will have it in front of me, whether or not we've done this correctly. Most of the time it's not, we don't need to check too much, apart from minor arithmetic errors. But when I'm just making something up off the top of my head, it's definitely good to check this. Okay. All right. So that's how this goes. Let's do one more example. So let C be, say minus 2, 1, 3, 5, and D be 0, 1, minus 1, 0. Okay. So let's compute C times D. Okay, so C times D. I'm going to do the exact same thing here, but here I can actually write it out because these are 2 by 2s, so it's shorter. So first of all, the question is, can I do this? Yes. They're both 2 by 2s, so the 2's match up, and also the resulting matrix is going to be a 2 by 2, right? Okay. So I take the first, so here I'm in this slot, so first row of C, first column of D. So minus 2 times 0 plus 1 times minus 1. That's in the first entry. In the first row, second column, again with the first row of C, second column of D now. So minus 2 times 1 plus 1 times 0. Okay. In this entry, I have, so this is second row, first column. So second row of C, first column of D. So this is 3 times 0 plus 5 times minus 1. And then last entry is second row, second column. So second row of C, second column of D. This is 3 times 1 plus 5 times 0. I'm just going to write this big enough so that you can see. All right, and so simplifying this, okay, this is minus 2 times 0 is 0 plus 1 times minus 1, so that's minus 1. Here I have minus 2 plus 0, so that's minus 2. And then I have minus 5 and 3 here. Let me rewrite this in a less stupid way. So this is the result, I believe. Yep. Okay. So that's C times D. Let's do D times C, since both of these are defined here. Okay, so D is 0, 1, minus 1, 0, and C is minus 2, 1. Did I say that's 3, 5? I think so. Okay, just rewriting them since I made a mess of these. Okay, so I'm just going to quickly compute these. So in this slot, this is 0 plus 3, so that's 3. And this slot, so this is first row, second column. So this is 0 times 1 plus 1 times 5, so that's 5. Notice I could already stop and say that these two matrices aren't equal, but I'm going to keep going. So next in this slot, this is second row, first column. So this is minus 1 times minus 2, so that's 2, plus 0 times 3, so that's 2. And then lastly, I get minus 1 times 1 plus 0 times 5, so that's minus 1. Okay. All right. Note. CD is not equal to DC. All right. There's completely nothing special about those two matrices. This is just how it is. Now, you might say, but wait, like they have the same numbers here. There's just some minus signs off here and there, blah blah blah. The thing is that this isn't. You're not going to be able to say anything useful out of this expression basically. So we will see some ways in which matrix product behaves nicely with respect to some things, but commutativity, being able to reverse the order, is not one of them. So matrix multiplication is not commutative in general. Now, sometimes it is, but for very special matrices. Okay. Now, I'd already spilled the beans on this, but just to show you a specific example, matrix multiplication is not commutative. A times B is not equal to B times C, or B times A, even in the event that even in the event that they're both defined. Note, this is from the homework. I believe I signed this. I hope I signed this problem. So from the homework. Some other nasty things. Okay. There exist matrices A, B, C such that AB is equal to AC, but B is not equal to C. Why is this a problem? Or it's not so much that it's a problem, but why is this not usual? So in order to try to develop your intuition for this kind of stuff, the way that you should always think about this is the following. So basically you should think about this as replace matrices with numbers, right? Just real numbers. And so the thing is that for real numbers, A, B, and C, do there exist real numbers, A, B, and C, such that A times B is equal to A times C, but B and C aren't equal? It turns out there do. Okay, there do exist numbers like that, but they have to be very special. Namely, A has to be 0, right? So, say 0, 5, and 7, right? So 0 times 5 is equal to 0, which is equal to 0 times 7, but 5 is not equal to 7. Okay, so this works for numbers too. Exactly, that is a problem. That is a problem. Okay, and so someone's already brought up the exact problem, which is A has no inverse. That is exactly the problem. So there's a number that has no multiplicative inverse, and that number is 0. That's the only one. Okay, but it's going to turn out for matrices, now that we've defined a matrix product, we can talk about inverses of matrices. Okay, and that's where we get into this this good stuff. Okay, but if A isn't 0, so if this number is not 0, if it's anything else, right? So A not 0. Now I don't want to write it as a matrix. So if I have a number and it's not 0, then A times B equals A times C means I can divide by that number, right? That implies B is equal to C. That's always true so long as A is not 0. Okay. So I want to think about reproducing at every step when you're dealing with matrix stuff. You want to try to bring your intuition to bear on the world of matrix algebra. You have to think about it in these terms. You have to think about it as, okay, what was the case here, and how is this going to differ, or how much does this fail in the world of matrices? So it's going to fail quite a bit for us, unfortunately. Okay, so couple of things here that I wanted to read off before moving on. So I'm going to bring the book here so that I don't have to copy down a long list of stupid properties. So let me make this slightly less blurry. All right. So here's a theorem 2. These are the properties of matrix multiplication. So it's the nice things about matrix multiplication. So if A is an m by n matrix, B and C have sizes such that this is all defined. So whenever I'm stating a theorem about matrices, that's always going to be what is assumed to be happening. That way we don't have to keep track of a bunch of subscripts. So A times B times C is equal to A times B times C. That's the associative law of multiplication. So that's saying that satisfies associativity. A times B plus C is AB plus AC. That's left distribution. And you can also distribute on the right. So B plus C times A is equal to B times A plus C times A. Right distribute. Now remember, because matrix multiplication is not commutative, you cannot swap the order of these things willy-nilly. You have to pay attention to the order. The order matters a lot. Okay, I mean, you just saw, we did an example where two matrices, you got a different answer, when you swapped the order of the product. Lastly, if you take a scalar multiple, a scalar, and you multiply it by a product of the matrix, you could have actually done that before the multiplication. So you could have actually scaled one of the or the other matrix instead, and that works for any scalar. It doesn't matter what it is. And then lastly, the identity matrix When you multiply by any matrix, on either side, so long as it works, you get the matrix itself. This is the identity for matrix multiplication. Now, this is really nice because it's saying why the identity matrix gets its name. So the identity matrix is the matrix that acts like 1, right? And I don't know why my camera's freaking out. Okay. So the identity matrix is 1 for matrix multiplication. So assuming that it's the right size that makes the product defined, i.e. I times A is equal to A, and that's actually the same thing as doing A times I. The reason you need to pay attention to both of those orders is that in general, for matrix multiplication, there's not a commutative property, so you can't or multiply it in any order. But for the identity matrix, you can. You can check that yourself if you want. Okay. Now, so the warnings, as I said. 1, A times B is not equal to B times A in general. 2, cancellation isn't possible in general. That's what I just said. So cancellation isn't possible in general, i.e. there exist matrices A, B, C such that AB is equal to AC, but B is not equal to C. Okay, and lastly, if A times B is equal to the 0 matrix of the corresponding size, this does not necessarily mean that A is 0 or B is 0. All of these properties hold true for numbers, but they don't for matrices. So if you have two numbers, if I tell you the product of two numbers is 0, then you can say, well, one of those numbers has to be 0, right? You can't have a product of numbers equals 0 and one of them not be 0. But for matrices, that definitely happens. Okay, see if you can come up. I don't think I assigned that one. I think I skipped over that problem in the homework. But you can look into that yourself. Try to come up with two matrices A and B that are not the 0 matrix, but when you multiply them together, you get the 0 matrix. So there's some really easy examples you could do here. Okay, so these are 3 ways in which matrix multiplication is weird. Okay, one more thing before I move on, and that's the transpose of a matrix. Okay, so definition. Transpose. Okay, so what is the transpose of a matrix? So the transpose of a matrix A that is an n by n matrix is the n by m matrix called A transpose obtained from A by swapping its rows with columns. What does that mean? It means the first row becomes the first column, i.e. the ith row of A is the ith column of A transpose. Okay. So, here's some examples. Say let A be 1 minus 2, 2, minus 3, 5, 0. What is A transpose? So A is a 3 by 2, so A transpose should be a 2 by 3. Let's look at the first row of A, that's 1 minus 2. That becomes the first column of A transpose, so 1 minus 2. So second column of A transpose comes from the second row of A, so that's 2 minus 3. And then lastly, the third column of A transpose comes from the third row of A, so that's 5, 0. Okay. All right. Okay. So this is an example, and of course, just to check, this is 2 by 3. Okay. All right. So this is what transpose looks like. What's some facts about transpose? Really quickly. So first, what happens if you take the transpose and you transpose it? You get back the original matrix itself. Okay. What happens if you have a sum of matrices? We'll assume that sum is defined, of course. A plus B, and you transpose the result. Well, it turns out this actually works in an unexpectedly nice way, and it's actually the sum of the transposes. That's convenient. Okay. What if you scalar multiply a matrix, C times A, you transpose that? Well, that's actually the same as just scaling the transpose, so it doesn't matter in what order you did that scaling. Now, the most important one, because it's the trickiest one, how does transpose behave with matrix products? It reverses them and applies the transpose. This is the trickiest one. Okay, this is the tricky one to remember. Okay, but it is important to remember this. Okay. Okay. So the transpose of a product of matrices is the product of their transposes in reverse order. Okay. So all this stuff we'll need later. We don't need it exactly immediately, but we need it later. Okay, so here's the thing. We get more paper here. Now, I want to be able to solve or algebraically manipulate matrix equations. So AX equals B, AB equals AC, etc. Things like this. Okay, so maybe this is what it looks like, the thing that we were interested in before. Maybe it's something that involves just a bunch of matrices like this, not necessarily vectors. Okay. What did I say? I said that we can't actually solve this or reduce this to say B is equal to C in general. Okay. So in general, I may not be able to do this. In a nice way. Or at all if we're talking about solve for some vector. So that's why I put solve in parentheses or in quotation marks here, because I just mean I'm doing some algebraic manipulations involving matrices. Okay, I want to be able to divide by A. Right? I want to divide by A. But how do I divide by A? Okay, this means I need a multiplicative inverse of A. Okay. What is the multiplicative inverse of A? I.e., we call something a multiplicative inverse if when you multiply by it, you get 1. But what's 1 in the world of matrices? It's the identity matrix. I.e., I want a matrix C such that C times A is equal to the identity matrix, and also A times C is equal to the identity matrix. Now, a couple of things. Those of you that have had some foundational logic stuff might notice that if I only used one of these things, so CA is equal to I or AC is equal to I, that's perfectly fine, but that's the notion of what's called a one-sided inverse, okay, which is not necessarily a two-sided inverse. But I specify, I require that this give me the same thing. I require that I have a two-sided inverse here. I'm not going to make that distinction any further. I'm just going to say an inverse. Okay, we call such a matrix the inverse of A. So the inverse matrix of A. And write that C is A inverse. Okay? So, this is what I want. Okay, unfortunately, this C doesn't always exist. Such a C does not always exist. First of all, what might you note here? The fact that I want both of these things to be defined means what? So, first goal, when it exists, I want to know how to find it. Okay, so when it exists, I want to know how to find it. Okay, this is my first goal. Now, I've already said it doesn't always exist. In fact, you might have noted something here. What am I going to require from my matrix in order for both of these products to be defined? Well, note, in order for both AC and CA to be defined, A and C must be what kind of matrices? They have to be squared. So someone said it in chat. They have to be square. So they must be square matrices. So if I want to have any hope of having an invertible matrix, I have to be dealing with a square matrix. So A is an n by n matrix if I want any hope of finding A inverse. But, warning, the following warning: not every square matrix has an inverse. So, there will be examples of square matrices that do not have inverses, unfortunately. So then the first natural question you might ask is, how can I tell, right? How can I tell if the matrix I'm dealing with has an inverse or not? Well, the answer to that will be 100% provided to you in Chapter 3. So that will be the entire purpose of Chapter 3, is answering exactly that question. Okay, but unfortunately, we're not there yet. We have to do some other stuff first. And so our focus is just going to be on trying to find one. So quick definition. We call a matrix A that has an inverse non-singular and a matrix that does not have an inverse is called singular. That's a little funny because I defined the negation thing first. Okay. But this is just additional definition. Okay. So, let's do cases. So, cases. Okay. So, we're looking at matrices that are n by n matrices. What about 1 by 1? So n is equal to 1. So A is a 1 by 1 matrix. What's a 1 by 1 matrix? It's just a scalar. It's just a real number. So every real number not equal to 0 has an inverse. Okay. So we don't care too much about about dealing with this because you've been dealing with this your whole life. This is 1 by 1 matrices are just real numbers. So matrix multiplication of 1 by 1 matrices is just multiplication of real numbers. And so you know exactly how that behaves. Everything that's not 0 has an inverse. Okay. All right. So there's the n equals 2 case. So A is a 2 by 2. What does a 2 by 2 matrix look like? Well, let's call it A, B, C, D. Okay. Now, there's a fact that you almost certainly probably know. So there's a big fact. Someone said, why not 0? So the problem with 0 is you can't divide by it, right? So exactly that issue you had before. 0 times 17 is equal to 0 times minus pi times square root of e, right? But those two things are not equal because you can't divide by 0. The fact that you can't divide by 0 is exactly the statement that 0 doesn't have an inverse, right? There's no number you can multiply by 0 to make it equal to 1. So that's why. But every other number you can multiply by something to make it equal to 1. So square root of 17, just multiply by 1 over square root of 17, right? Okay, so a fact here for a 2 by 2. So if A is the 2 by 2 above, and if AD minus BC is not 0, then A is invertible. And A inverse is 1 divided by AD minus BC times, do you remember how to do this? So A and D swap. So AD on the diagonal become DA, and you negate the off diagonal terms. Okay. And so I have this nice formula for the inverse if this condition is satisfied. Now this might seem like complete magic or voodoo or something because this literally just comes out of nowhere, but we'll see where this comes from later. We'll see where this comes from later. Okay. All right. So, what is the idea here? When I say we'll see where this comes from, I mean this condition, and I also mean this formula. Okay. So this formula is actually the special case of a more complicated formula we'll talk about later. This condition, some of you probably already know exactly what this condition is. The condition that we got for the n equals 1 case, of course, was even simpler. It was just the number itself is not equal to 0. Here, it's some complicated expression involving these things. What about in the n equals 3 case? But if that complicated expression is not 0, right, then our matrix is invertible, and here's the formula for it. So here's an example. For 2 by 2 matrices, it's very easy. So let's pick a matrix. Let's do something like 4, minus 7, 0, minus 1. Okay. So what is A inverse? So first I check what is AD minus BC. AD minus BC here is 4 times minus 1 minus 7 times 0. So that is minus 4, which is definitely not 0. Okay, so A inverse is 1 over minus 4 times the matrix where I've swapped 4 and minus 1, and I've negated the off-diagonal entries. And now I need to multiply these things to move the scalar inside. So I have 1/4 minus 7/4 0 and minus 1. So let's check. Let's check that these two things are actually the identity. So A times A inverse is, so here we're checking. So A times A inverse, I get first row times first column here in this way. So this is 4 times 1/4, so that's 1, plus minus 7 times 0, that's 1. The next entry here is first row, second column. So first row, second column. I get 4 times minus 7/4. Okay, so that's minus 7. Plus minus 7 times minus 1. So that's minus 7 plus 7. So that's 0. Right, and the next slot. So this is second row, first column. So I get 0 times 1/4 plus minus 1 times 0. That's 0. And then lastly, I get 0 times minus 7/4, so that's 0, plus minus 1 times minus 1, which is 1, which is the 2 by 2 identity. So yes, that is in fact the inverse. I didn't just lie to you. So the inverse of A is this matrix. Okay. All right. So that is the 2 by 2 case. Thus, we have a simple formula for the inverse of any 2 by 2 matrix that satisfies AD minus BC is not equal to 0, right? Oh, I'm off screen. Yeah, so we have a simple formula for the inverse of any 2 by 2 matrix that satisfies that condition. Okay, so that's nice. Of course, if it doesn't satisfy that condition, then it doesn't have an inverse. So if it doesn't satisfy the condition, i.e., if AD minus BC is equal to 0, A is singular. Okay, so that's for a 2 by 2. All right, and so we have a complete description of every type of 2 by 2 matrix that has an inverse. If it satisfies this condition, we have a formula that just tells us what the inverse is. If it doesn't satisfy this condition, then it's singular, i.e. it doesn't have an inverse, i.e. it has no inverse. And so that completely describes what it is that goes on. So I have one more case I want to discuss. Case is n equals 3 and larger, of course. So I don't have enough time to start here, so what I'm going to do is just say one thing, which is, unfortunately, there is no analogously simple formula for the case of a matrix that's an n by n matrix where n is greater than or equal to 3. Okay. There is a formula that is similar, but it is not simple anymore. So that's the issue. So there's not going to be some straight formula that I just use to spit out the inverse. So we will have to find it. Okay, we will have to find it in a longer way. Okay. All right. Although typically I won't have you do this for anything worse than like a 3 by 3 because doing it for 4 by 4s and 5 by 5s is just insanely tedious unless it's a really, really convenient matrix. Like it has to be really doctored up to be just perfect. Okay, so anyway, that's all I wanted to do today. Can Gauss-Jordan form augmented matrix to B equals identity? Yeah. So the thing is that if you're talking about, so I mean, we are going to talk about the Jordan canonical form later. I'm actually not gonna do partition matrices, even though it's 2.4 in chapter 2. I'm not gonna do that until later in the course. Anyway, there's a way called the adjugate formula that is the analog of the 2 by 2 case, but it's not nice anymore. So in order to do this, we are going to have to do as someone said, get Gauss-Jordan form of augmented matrix with B equals identity. So basically, you are setting up a particular augmented matrix that's not, it's a special augmented matrix, and you're putting it into reduced row echelon form, which basically turns it into, on one side you're going to have the identity, on the other side you're going to have the inverse. So I'll talk about all that stuff on Monday. That doesn't make any sense, so I'm not going to write it out now because I don't have time, but we'll talk about all that stuff on Monday. So your homework is due on Monday. So Monday night, I'm going to have office hours. Monday afternoon, I will send you all the link when those happen. So I'll send you the link like 5 minutes before. But anyway, so that's the deal. I'll see you all on Monday.